colleagues. Welcome to the last day of our advanced medical 3D printing FTP program. Our today's first speaker, Dr. YRK sir, is handling the 3D printing in complex oral and maxillofacial surgeries and all. Some of his experience, what the printed with the patient specific and implanted with some of the patients in collaboration with some of the medical colleges, is going to give us his experience in this field. It's my pleasure to once again introduce our speaker. Dr. Y. Ravikumar is an associate professor in the Department of Mechanical Engineering at NIT Warangal and is the coordinator of this FTP program and all. He has been working in this 3D printing more than 15 years, and when it was started as a rapid prototyping, he obtained BTech from Mechanical from JNTU Kakinada during 2000, ME in Computer Integrated Manufacturing from PH Technology Coimbatore, and PhD in Mechanical Engineering from University of Osmania, and postdoctoral from Milwaukee School of Engineering, USA in 2012. And he started first MTech program in India in collaboration with CMTA Bengaluru during 2014. And he established a world-class 3D printing laboratory at NIT Warangal under the Tech Phase 3. He has published more than 60 research articles in national and international journals, and he has filed a 1 international patent and 2 Indian patents in the area of 3D printing. He has conducted more than 15 training programs across the India and trained around 900 participants in the area of 3D printing. He received Young Engineer Award of the Year during 2009 from the Government of Andhra Pradesh and the Institute of Engineers. His research interest includes the 3D printing, additive manufacturing, BioCAD, and bioprinting technologies and all. I welcome to this session, sir, and thank you for giving your experience in this 3D printing with respect to the medical application, especially the complex oral and maxillofacial surgeries and all. I welcome you once again, sir. Over to you, sir. Thank you.
Yeah, thank you, Dr. Manjaya, for your introduction. The participants now, as we are come to an end, means like we are at the last day of the FTP, and so far we have learned about several aspects of 3D printing, in particular to medical applications. And in continuation with that, now this printing in complex
Sir, we are not able to hear your voice.
Is it? Hello, my PPT is visible.
Yes, sir. Yes, sir.
Yes, sir. Only voice you are unable to know.
Yes, sir. Now it's fine, sir.
Hello.
I think some delay. There's a delay.
There is a delay.
Yeah, there is a delay in voice.
Okay, then can I switch off my video? Maybe bandwidth. I don't know what is the issue. The problem with the video. Hello. Now is it okay? Hello.
Yeah, now it is fine, sir.
Okay. So yeah. Very good morning, one and all. So now we have come to an end of this program. That is that today is the last day of this FTP, and so far we have learned things about 3D printing, in particular to medical applications, say how to design, how to model, how to analyze, how to print it. So we have, say, heard from the hospital people, like a couple of surgeons, and we are going to hear one more surgeons convert your DICOM images into the STL file or any 3D printer understandable file formats. And today's session, so I'm going to share my experiences with our collaborators. So from the dental surgeons and even oral maxillofacial surgeons and the craniofacial surgeons to whom we have worked.
Sir,
And yes, hello. Yes, Sai. Hello. Hello. Am I audible?
now it's audible, sir. Till now, we didn't hear your voice.
Can I rejoin? Otherwise, I don't know what is the.
Sir, try it once, sir.
Yeah, let me rejoin.
Yes.
There is some issue. Hello.
Yes, sir.
Is it audible now?
Yes, sir. It's audible.
Okay. Can I share my screen? 1 minute. Are you able to see my screen?
Sir, it's loading.
Okay.
Yes, sir. Now we are able to see it.
This PPT and then the slideshow as well.
Now it's fine, sir.
Okay. Okay. Very good morning, one and all friends. So this session will be on 3D printing in complex oral and maxillofacial surgeries. This is going to be the personal experience, our personal experience with the surgeons to perform the surgeries on the various complex oral maxillofacial surgeries, as well craniofacial as well as dental surgeries. Also, it has been included in during my presentation. So I'm going to share my experience with the hospital people, the surgeons in these areas. So how these 3D printed models or implants has been used for serving the needy people in the healthcare. So coming to the outline of my presentation, so I will quickly introduce this medical 3D printing technology. It doesn't require much introduction. By this time, like for the past 4 days, you are very much familiar about this medical 3D printing practice. And let me quickly give an overview on this, and then the 6 case studies I'm going to discuss for this session. That is, the first case study is a cranioplasty case study. So how 3D printing is helpful for modeling and analyzing the cranial implant for a patient-specific requirement. So as we know that this technology is very good for say customization and the personalization services. So of course in medicine that is very much needed. Each case is a unique, each case is a special case or a unique case, rather than which they are not able to generalize these cases like which we have some standards in engineering, but definitely they don't have such a standards. Why? Because each patient may be the unique reasons for the disease, or maybe trauma, or maybe say some fungal infection or anything. Like it may be a infection, or it may be a kind of say any reasons for the disease. So but they cannot say generalize this surgeries. So then each time it may be a challenging for a surgeon to operate. Even we heard from two of the surgeons previously also, like how complex some of the surgeries through a conventional methods. But definitely 3D printing with the integration of the 3D printing in the surgical say procedure, so they are going to get a lot of benefits. So the one thing, as we know, that it is very good for the personalization and the patient specific implants. So then we are going to see the first case, how it has helped in the in cranial designing and the modeling and analysis of that implant. So the cranial is the bone, the skull bone, which protects the brain. Normally that portion is called as a cranial, um, the bone, cranial bone. So we are going to discuss how 3D printing helpful in this case. And the second case I'm going to discuss here is a dental case study. So how this technology helpful for fixing an implant and designing and fixing an implant for a dental case study. So how this technology helpful, rather than the conventionally taking an impression from the patient mouth, and those conventional methods may have a certain challenges, but definitely this 3D printing helped them to right placement of the right positioning, right say size, orientation, all that has been achieved through 3D printing. The second case study we are going to discuss is a dental case study, and the third case study, it is a mandibular distraction osteogenesis. So this is the one kind of a surgical procedure where say you have say mandibular means it's a lower jaw. So they have a procedure distraction osteogenesis. So distractor is a device, so which guides the bone growth. So osteotomy or osteogenesis is nothing but say cutting the bone and allowing the bone to grow. So then bone growth will be varying from patient to patient and age and gender and several factors. So then how 3D printing helpful for say for a distraction osteogenesis surgical procedure? That is the third case I'm going to discuss. And the fourth case, it is a cancerous bone reconstruction surgery. So how this technology helpful for say operating a cancer patient who needs to be removed a lower jaw, and then it should be a bone grafted, or it should be a say implant as to be. So the fourth case study I'm going to discuss here is so that is the reconstructive surgery. And the fifth case study is a temporomandibular giant oncolysis. So that is say this is one of the complex surgeries which you can even heard from the previous surgeons talk. So the Tmj Angolysis is very challenging for a oral maxillofacial surgeon. So then how this technology helpful for designing right from the scratch this joint, uh, and then how it has been helped in placing the implant to the patient, say a human body. So this is the fifth case I'm going to discuss. It's a TMJ Angolysis. And the sixth case I'm going to discuss is a basal osseo integrated implant. So this is an accident case, and who needs um, a what you call a indigenous or a patient matched or patient specific, which the standards size implants so that are available in the market, those are not say um, work out for his condition of the fracture because of an accident. So then how this technology helpful for designing a basal osseo integrated implant, so which is indigenous or which is a unique, which is only for that, means it's a kind of a bespoke kind of a design which is specific to that patient. So that is the sixth case we are going to discuss. And of course, the so far we are using, as we understood, the bone replacement or the bone substitute, means majority of the time your 3D printed implants or the device or the prosthetic, so it is going to say substitute the functionality of the bone majority of the time. So which so far we are, but as we know that this technology has been matured and it is going towards printing an organ. So is it so easy, or what is the state of art of this organ printing? That's what I want to conclude with this final topic. So that is organ printing. So this is what I have planned for the next 1.5 hour my talk. And let us quickly introduce this medical 3D printing. Just is a overview, like probably you may aware or you came to know during this FDP what is the general procedure of any medical 3D printing practice. So it should start with a CT, MRI, or a PET, or any. It may be an invasive, or it may be a non-invasive, means like say sometimes you may use some endoscopy or any invasive device to say to pass inside the patient and getting captured the images. So not all the time through a kind of non-invasive, but sometimes even it could be an invasive kind of say the diagnostic method normally you come across. Then that is also very well taken as your say start point of your journey, the medical 3D printing journey. So let it come to a CT, MRI, PET, or angiogram, or any otherwise any invasive kind of acquisition system. So then you have every say diagnostic say devices, you have a provision of saving them as a DICOM image. So then you take the DICOM image of the patient information from the radiologist, and then you are able to say process that say DICOM images so that are there by either using a commercial available softwares or by using open source softwares. And as for your say convenience or the facility that are available, then you can be able to process those images. Why you want to process those images? So as we know that it consists of several tissue information, but you may be looking at a particular tissue or a particular say um, organ, a particular region of interest you may be looking at. So in that case, which you may adopt these medical image processing softwares to segregate your bone of interest or a tissue of interest or the region of interest or the organ of interest. So then once you pick that, so then you are able to reconstruct these two-dimensional images into a three-dimensional model, and which could be further understood by the 3D printing technology. So that's what where you are able to do it. So once you convert that as a 3D print, 3D reconstruction of the model, and which is now as a CAD model or now as a STL file or whichever format that you are the existing printer that is supporting, then you are able to comfortably so import that data to your say software which is connected to your printer. So a kind of interfacing software which you can get it from this vendor or a open sourced, it has been integrated to your printer. So then your journey from here onwards, so then you are comfortable with say applying the process parameters based on your say the availability of the material and then the technology, and considering the design aspects of 3D printing, and you are able to say design in the last class means the Srikanth was explaining then how do you create a supports or how do you say fit, put your fill density or various parameters, like say you can have a different toolpath strategies. So how do you say optimize these things? So even without the optimization also by default software may give, and then you can go for that. But definitely if you want to looking for optimizing these resources, definitely we need to work on those process parameters and come out with the optimum set of parameters. And once you have generated that say build setup or the cross-sectional images, so that is needed to run the machine, so in a layer wise fashion, so then you send that data to the printer. So now where your printer now depends on your application. So then you have to choose a right printer, right material for your medical application. So material is very important, as we know that not all engineering materials are qualified for the medical applications. So then you have a certain materials, it may be getting eliminated because of these stringent requirements of biocompatibility or bioresorbability or any other properties. So then we need to so select an appropriate technology and appropriate material to perform the printing. And once you get printed your parts, so now you can make use of these models. So maybe the first level of application may be just for diagnose the disease of the patient. So that is the initial level, or just to say know about the disease or to analyze the disease. So then you may use these models, or even you can take these models, you can give it these models to the surgeon to plan the surgery or rehearsal the surgery, or intraoperatively they can take these models into operation theater, and they can resolve any complex surgical treatments into a more simplified treatments. So then you can either use them as a models or prosthetics. So which you can see there are some artificial limbs, or the say somebody has lost his nose or the ears or the eyes or the say skin or wherever. So then we need to oftenly looking for a prosthetic, then that is patient specific prosthetics. That is another application where your 3D printed models, as such, it has been used for prosthetics or for planning the surgery or rehearsal the surgery or implantation or device or a template or fixers. You can use in several folds. So depending on the patient condition and consulting with the surgeon, so then accordingly you can make use of these models once it is getting printed. Now you are talking about the bioprinting anyway, then we will talk a bit on that also. And we are going to have another speaker today. He's going to even give a lot of insights on the bioprinting. Then this is the general procedure normally to come across any medical 3D printing practice. And though you have, say, a lot of tools now, virtual reality also has come into picture, and you have a lot of advanced CAD tools, but still, why you are looking for a physical model? So, a physical model as a physical model which have a physical feel, and that is the area of interest where you are targeting it. So you have that freedom. Like say, for example, if you take this case, so who needs the oral maxillofacial implant here? So then in that case, how complex is this surgery to communicate even with the other surgical teams? Like say, you have orbital rim here, and if you are not placed this implant, say, which is in aligning with the rest of the orbit thing here, they are unable to place the eyeball in the right place, and definitely there will be a chance of losing the vision of this patient. So then you have to invite the ophthalmologist and the oral maxillofacial surgeon, and sometimes a neurosurgeon can also be the part of this surgery. So in that case, how your 3D printed models, the physical models, how it's getting helped. So definitely either it could be a oral maxillofacial or a pelvic region or a femur region or a spine region or a cranial or a bone or whatnot. Like say in every say part of your bone or the anatomy, human anatomy. So these models are now it's quite encouraging for the surgeons. So then that is what where we are talking about to communicate the surgical teams, in this case the ophthalmologist and the oral maxillofacial surgeon, and even you can better educate the patient on showing these models. So we are going to put an implant, we are going to work on this side. So you can very well explain this, or you can very well communicate with these models. So that is the thing where you're going to get out of these physical models rather than a virtual models. Normally, you work, or the images, two-dimensional images. Normally, they work. Then even it can be assisting the surgeons with diagnosis. Um, Planning means there should not be any surprise for the surgeon while operating. So there is a complex case that he is going to operate, but definitely these models will enable the surgeon to better plan the surgery. Say what he is going to do is having a better idea before he stepping into an operation theater, and there won't be any surprises for him during this surgery. Why? Because this will help the surgeons to say have the lot of confidence levels he or she is going to before he or she step into the operation theater because of these confidence levels that they have already worked on these models. That kind of a confidence levels are high. So, and then they can very well plan, take the devices or say what sort of instruments they need to carry, or the implants or the prosthetics if it needed during the surgery. So they can very well take that, and then they can that is then opportunity for a surgeon, and even they can rehearsal and they can simulate the surgery. So again, like a design is all about iteration. Even surgery is also not like a single step or like the best surgical procedure. You never say that whatever the surgeon has performed the best surgical treatment, right? So then there won't be such kind of a thing, and still there will be a chance of improving the surgical outcome or the rehabilitation of the surgery. But definitely it is an opportunity for the surgeon to do a lot of rehearsal on these models and simulate it, and he may come out with an say innovative surgical procedure that has been not done before because of these models that he's going to operate and use it. So that will help him to come out with sometimes as a innovative surgical procedure, not like so definitely we have heard from the previous surgeon, one of the surgeon has spoke like so these models are it is almost giving an on par opportunity for a junior doctor with a senior surgeon because of these technologies which a junior doctor can also able to better expose the site or the region where they want to operate work on that. So then that's a good opportunity for them to even come out with an innovative, or maybe a junior doctor or maybe an experienced skilled surgeon. Then there is an opportunity here to come out with an innovative surgical procedure with these models, and even it will also create a customized prosthetics. So that's what, like say, which we have already discussed, like say one patient has lost his ear or the nose or the eyeball or the eye or hand or a leg or everywhere anywhere, like there is a prosthetics, so which it is unique or which it is specific to that patient. So all these anatomies are not unique one patient to other patient. So then even you can customize these prosthetics maybe by integrating your reverse engineering technologies plus 3D printing. So which you are unable, we are able to do this kind of customization of the prosthetics, not with 3D printing alone. So the 3D scanning or the reverse engineering techniques can also help in designing these customized prosthetics for the patient specific prosthetics. And you had opportunity to accurately place these implants. That is always there, of course, because of this say patient specific data and the patient required implants which is specific to him. So you can accurately place these implants because of these reasons. So then you have this an additional advantage with the physical models. You can keep on talking about the various physical advantages of the physical models. But then how do you get manufactured this? Of course, 3D printing. And before we go to that, a bit of biomaterials knowledge is needed. Why? Because so as we already know that not all the engineering materials are qualified for the bio applications. The reasons, if you see the biomaterial definition, which is given by the standard organization. So the definition of the biomaterial, it is a synthetic material, as we and everybody knows that it is a man-made material that you are going to say place inside the human body. Basically, it is a man-made or a synthetic material, so which is used to replace or restore the function to a body tissue, like it may be targeting to a bone or any soft tissue or even any vascular thing or nerve or any tissue that you are intended to replace or restore the function by making use of this the material, and it may continuously say or intermittently in contact with the body fluid. So it may be continuous or intermittently it is contacting your the biomaterial that you have implanted in the human body. So it is continuously or intermittently in contact with the body fluids. So maybe blood, maybe cerebrospinal fluid, or any body fluid that you come in your human body. So it is getting, contacted. So then the first and foremost requirement of any biomaterial, so it should be must be a biocompatible in nature. So what do you mean by biocompatibility? So it is not elicit any kind of say adverse response from the body. Means it should not either from the body to the implant or implant to the body. So it should not say have any such kind of adverse response. And it is also say non-toxic and non-carcinogenic, means it should not create any say harmful things or the cancerous say things to the human being. So that is another thing. So because of these stringent requirements, so majority of your engineering materials are not qualified for the medical applications. So that is the thing. And apart from this biocompatibility and the toxic, non-toxic, and non-carcinogenic, it also must have, say, sufficient physical and mechanical properties to serve as your, say, replacement of the body or the augmentation of the tissue. So it must have the same property, or it must have the same physical, mechanical property that your biomaterial with on par with your native body tissues. So that is another challenge, or that is another requirement from the biomaterial. And practically it should be so amicably it should be formed or machined or fabricated any different shapes. Why? Because human anatomy itself is a very complex anatomy. You have a lot of neurovascularity undercuts. So you have several of them are more complex. And then how you are going to shape them, these complex, say, into a kind of uh, say how you're going to relatively ease of making these or forming these or fabricating these. So and it has to be a low relatively cost is also a matter which it should not become much expensive also, and it should be relatively cheaper and it should be readily available. So these are the some of the requirements from the biomaterials. And so ideally your biomaterial should exhibit so biocompatibility, that is chemical composition, anything. It should avoid any tissue reactions to the body or vice versa, and excellent resistance to degradation. Means if it is made out of say metal, it should be corrosion resistant, and it should be, if it is a polymer, it should be resistance towards say biologically degradation. It should be resistive to that, and it should acceptable strength to sustain your cyclic loadings, especially you have an orthopedic applications where it may be subjecting to a lot of cyclic loadings. So then it should withstand that cyclic loadings, and it also a low modulus to minimize your bone resorptions, and high wear resistance to minimize your wear debris generated. This I picked from one of the handbooks of materials for medical devices. So then with this background, like say you have say these you talk about the biomaterials. So biomaterials have a lot of scope to implant into the human body, right from the ear parts to the dentures to the tubes to the pacemakers to the kidneys to the heart, say, and then you have the sutures that have been also used on finger joints, blood vessels, knee joints, bones and joints. So you have a lot of scope of these biopolymers. So that has been used for the several purposes, right from the joint replacement to the sutures to the say ophthalmologist for the even drug delivery systems. So you have all these poly group of polyethylene, polypropylene, PET, polyamide, PTFE, polyester, and you have polyethylenes, PVC, PMMA, silicons, and hydrogens. So these are some of the biopolymers. Even majority of them can be 3D printed now with the latest advancements or the latest technologies that you have in the recent times. So you can have all these body parts. So it is an appropriate material, can be used and a right material to the right organ or the tissue. So this I picked from one of the handbooks of this medical devices. So then you can go through afterwards also if you can have these the material and the appropriate tissue or the say the kind of body part that you're going to work on these biopolymers. And further talking about the metals and metal alloys, 316L stainless steel. The well-known AM fabricated metals and metal alloys has been listed here. 316L steel, that is for fracture fixation stents, surgical instruments. And say you have say commercially pure or aluminum vanadium, so you have 6,4 or 6,5, and you have several compositions of the titanium compositions you have with other say materials. So you have for bone joint replacement, fracture fixation, dental implants, pacemakers, and so on. And cobalt chrome is another alloy, like where you have for a lot of bone and joint replacement, tensioning, dental implants, dental restorations, and heart valves. And nickel titanium is also for bone plates, stents, orthodontic wires. And you have precious materials like gold, silver, platinum, and you have amalgams for dental restorations. So you have some of these metals and metal alloys for the medical, as well as it can be done through 3D printing. And you may have bioceramics and glasses, like you have aluminum for joint replacement and dental implants, and zirconia for joint replacement, and calcium phosphate for bone repair and augmentation, and surface coatings onto the metals. So this can be used as the coatings purpose, the calcium phosphate. And you have bioactive glasses for bone replacement, and porcelain for dental restorations, carbons for heart valves and the other devices and dental implants. And biocomposites may be a quartz silica fillers with for the dental restorations, or the glass fillers with PMMA, that is again a dental restorations, otherwise called as a dental cement. For fillings normally use this material. So these are some of the polymers, metals, ceramics, and composites, and that is readily available with the 3D printing practice. And of course, you do have several applications. So right from the orthopedic total hip replacement to dental implants, cranial, maxillofacial. These are the three areas our experience I'm going to share. And it can be used as a device, biomedical device. And the biosensors can also be fabricated through 3D printing. And biomems devices can also be done through 3D printing. And microfluidic devices for bioseparation and bioprocessing can also be done with the 3D printing. And augmented tangible molecular models for R&D purpose. Even the other day, Dr. Reddy was explaining his anatomical models for the teaching and say for the anatomy class, or for this bones, how they are making use of 3D printed rather than working on a cadaver bones, which it requires a lot of preservation problems and a lot of smell it may come and all that. So it even you have this technology to make use of these applications. So that is a wonderful opportunity for making use of these 3D printing models. Nowadays, you have a lot of material, multiple materials, multicolor, transparent materials, 100% transparent materials are available. So it will help a lot for the R&D or the anatomy classes. It is quite, say, encouraging. And you have, say, a conjoined twins, such a complex surgery, as it will make very simplified because of the 3D printing technology. And you can even use this technology for what you call the facial reconstructions or the cosmetic surgeries to come out with a symmetric, say, um, appearance of the patient, so that you can say do it. And then you have these reconstructions, facial reconstructions, or the cranial implants, designing, fabrication, developing, and finger joint developments, knee joints, femur joint, oral maxillofacial, or prosthetics that you can design, fabricate, and then fix it, and a lot of orthopedic applications, and of course the pelvic or the femoral joints. So it is quite, say, you can find tons of literature in this area to they make use of this technology for these purposes. So right now we'll be concentrating our experience these three areas. But though we don't have much experience with the other areas like orthopedic and the other areas, but even we do work with some of the heart surgeons to make some devices. But anyway, at that I'm not going to present here at this point of time. I'm going to say concentrate these areas and our personal experience in these areas. And the first case study, it is a cranioplasty modeling and analysis of the cranial implant. So then how this is helpful for, say, designing a cranial implant. So this case is an accident case, who needs a cranial implant. So the biggest challenge for a surgeon is how do they design this implant, which is going to fix it here, and it should be biomimic the bone nature, bone structure, bone geometry, dimensions, all that. So that is the challenging one, and the thickness of the skull is not uniform across the say structure, but that is the another challenge for these people. So which we need to even use this, um, say we have started our journey with taking the images in a mimic software and segmenting it. So which we have already demonstrated you how you can segment these images. So based on your say region of interest or the bone of interest, by choosing an appropriate say threshold number, or the Huntsfield number, or the CT number, or basically that is in proportion to your say bone density of your tissue, the density of your tissue, basically whether it is a bone or a soft tissue, or within the bone you have a huge range of this the CT number or the Huntsfield number. So then you can so pick your region of interest is the damaged portion. So then which we need to say design an implant for that region. So then for that region, you need to do several measurements onto this skull part, or even we need to design an implant freshly. So then you can adopt a CAD CAM software here, or we have used a software called Trimatic to design this implant. So you can, based on your availability of the tools, software tools, so then you can use an appropriate tool to say to come up with your design. So means we have designed a cranial implant. So this is a unique or specific to this patient condition based on the geometry and the form and other fitment to related to this patient's specific thing here. And one more thing here is it should have a tight fitting. The fitment of the implant versus the native skull bone, so that should be happen properly. Why? Because you have a cerebrospinal fluid, so that will say pass all the way from your say brain to a spine, so it will be pumping, or it will be say circulating. Then you need to carefully design. Why? Because you have a brain very adjacent to this bone, the cranial implant. Rather than right now you're going to say implant it here, so designing and fixing it here, then you have to be say take care about that body fluid or cerebrospinal fluid. So then we have come out with a different say the designs to come check with the fitment. So we have a skull say anatomy or the reconstructed model, and that is versus the designed implant. So then we have tested for the fitment and analyzed for the fitment. So this we have published in one of the journals. So if somebody is interested, you can for that channel. And even further, we have done a study on say how do you model and analyze or the structural analysis of the skull, the cranial implant skull versus this cranial implant, so which is beyond the midline deformation means. So not all the times your defects or the damages of or the maybe trauma, maybe disease, or maybe say fungal infection or whatever it is, like say it need not be every time a symmetric deformation. So it may be sometimes beyond the midline deformation you are which we need to do. So in that case, what we have done is we have developed our own algorithm to come with this reconstruction of the surfaces through a nerves-based algorithm to do that. So the normally, if you have a symmetric defect, you can make use of the mirroring command, and you can take uh, the survived copying the survived thing to the defect side, and in that way you can go about it. But if it is not possible to do that, and sometimes which we need to come out with our own say algorithms we do to write and then to reconstruct these surfaces. And another thing is like say how do you get fixed? This means ultimately your implant has to be fixed onto the skull bone. So where we need to you fix the screws, so the placement or the number of fixation points. So that matters a lot. Your say the pressure of that body fluid onto the implant. So that is going to matter a lot here to the placement of this say so then we have come out with optimized placement and the optimal number to fix this implants, the fixation points to the implant to the skull bone. So then we have done that sort of analysis here, and we consider the materials like biopolymers like PEEK is one of the polyether ketone, and you have polymethyl methacrylate PMMA. And from the metal group, then titanium 6,4 has been considered, which is more say easily processed onto the facility which we have. And this is what we have done certain deformation studies and equivalent stresses studies on these materials, and further which we need to say finally print them this implant. And this implant now, which we can see, it is not the uniform cross section across the bone. Like you can find a sandwich kind of a structure here, like say, which you can see. You have three layers of say bone. Like you have the inner bone maybe around 0.7, 0.8 mm thickness, and the outer bone around 0.4, 0.5 mm thickness, and in between you have this apodal porous kind of nature. Means this is the altogether you have a different composition of the bone, that which you are going to mimic this as for the patient condition. So that is the thing where we have come out with this lattice based designing here to match the patient specific structure, the bone structure of the patient. And then we have further published this into a journal in a medical and biological engineering and computing. So we have come out with a homogeneous scaffold based modeling aspect for your cranial and the skull. So we have come out with a unit cell algorithm, a meshless approach we have developed and we have published here. So in this way, however, 3D printing technology helpful for modeling and analyzing a cranial implant that is a unique or a bespoke to a particular patient requirement. And then we have the second case study. This is the dental, say, implant fixation by making use of this technology. So then how it has helped us to solve this kind of so we consider a 19-year-old boy patient, male patient, who needs a missing tooth here and requires an implant. So normally what they do is they will take an impression from the mouth. So that is a POP kind of thing. And then by taking the impression from the mouth, they could able to get only the outer surface information, but they never get the information about the nerve. That nerve will pass through this condyle portion, and it will touch the mental foramen, and again it will come to the other side of the condyle portion of the jaw. So the biggest challenge here is he has to drill a hole here to fix the screws or the implants to the patient mouth, and fixing the abutment, and on top of it the tooth, they have to fix it, and for that matter they have to drill a hole. And during the process of drilling a hole, if they are using a POP models, so they never get this information about the nerve. So, and then there will be a chance that they may over drill or they may under drill, and sometimes they may damage this nerve also. Then how the 3D printed models are helpful for getting the information about this nerve, and as well as allowing the dentist to perform a mock surgery, or rehearsal the surgery. Say what is the best the size of this drill, and the orientation of the drill, and length of the drill, and so on. So all that parameters has been, say, practiced on patient specific models that has been captured from the patient own patient body, means by collecting a CT data. So then you collect those CT data, and then you can, say, take the region of interest and you print these models, and which you can see this nerve information in through these models. But nowadays we have more 100% transparent models, like say you have epoxy resins, maybe from DLP systems or SLA based systems. So this we have used the FDM technology only, but normally the FDM technology you cannot find more transparent material. But nowadays you have a certain transparent materials also, but not 100% transparent. But this we have done almost 12 years, 13 years ago. But now you have better technologies and better materials and better properties of the materials. Even it can further explode for this say the implantation. So then take these models and sit with the surgeons they are going to say, they let them rehearse in the surgery on this model, like say what kind of a drill bit size they want to, like the counter drill and the finished drill sizes. Let them practice all that things, not during the surgery in the operation theater. Let them practice all that here, say by using their regular dental drills to how they are going to operate during the surgery. So let them do that practice here onto the biomodels regarding the size of the drill, the length of the drill, orientation of the drill. All that will be planned here and the rehearsal here. So once they have done those rehearsals, so based on the outcome of this mock surgery, so they can directly go to the say operation theater, so where they have that confidence levels. Otherwise they should have say practiced or based on the images that they have, and based on that they used to operate it. But now you have customized your say implant as well as this entire surgical procedure, like say the drilling of the hole, what is the size, depth, and what is the orientation. All that has been already done well before the operation theater they reached, and they have done that. And then based on that say the outcome of that mock surgery, so then they perform this real-time surgery and fixing these implants and checking the post-operative the positioning of the implant, how it is getting, whether it is getting placed correctly or not. So all that will be say done on these models. So in this way you can provide a customized solution to the patient required things, but not taking a standard sized implants or standard sized drills to, or say experimenting onto the patient. But now this is a kind of opportunity for them to work as for the patient condition, as for the requirement. So then you can better use these technologies for better outcome of these surgical treatments. So in this way we can detect that. And the third case study I'm going to discuss here, the mandibular distraction osteogenesis. So this is a one kind of surgical treatment. Osteotomy or osteogenesis is cutting the bone. So then you do cut the bone, and bone will be having its own natural growth. Again, depends on the age, gender, and other factors. But anyway, they do use a distractor device here to guide that bone growth, and that has been done in a mandibular, means it's lower jaw. This is what. They are going to use this surgery. And this is we have done with the collaboration with Dr. Aditya, which has shared his experience in the previous session. So this is the thing where we have done with him, which we can see this girl right from the birth. She had a facial, say, deformity, or the bone growth has not happened properly. So because of that, you can see the facial uh, asymmetricity as well as normal opening is 5 to 6 centimeters of a healthy person, but she could not attain that normal opening. And altogether, they have to perform a surgery here, which is of say which they have to reconstruct this bone. Means what they do is, so conventionally they do take the images, and based on the CT images they design this distractor or that instrument to guide the bone growth. But here we have an opportunity in terms of 3D printing to print the patient specific, or the as per the patient anatomy. You are able to print that the deformed bone as a model, use that to design further your devices. So this is the abnormality which you can see in the other say views. You can see she had, because of that facial deformity, you can see together. Yeah, and then what we need to do again, we need to start with taking a CT data of the patient that we have imported into the Mimic software, and we have used that tool segmentation, region growing, thresholding, or whatever the tools that are available, region growing and other tools, and then the region of interest from the skull to only mandibular portion is needed for this pair condition, and we doesn't require the spine, and then we know how to create a mask and how to say uh, region grow and how to detach or other tissues or the which is focusing to only the region of interest. So then we are able to pick that region of interest, and further this has been converted into STL file, and it is getting printed, and it has been given to the surgeon to design that. It's called distractor. This is what I'm talking about. This device called as a distractor. So this distractor, what it will do is the function of the distractor is you have a kind of a screw kind of a setup here. So it is simply a rotational motion has been transferred into the linear motion of where you have this thing. So then how much uh, how many revolutions so that it needed, and what could be the stretch that we need or the twist that we need to do. So then by cutting and leaving this gap in the bone, so then you do have internal distractors, and some of them are external distractors. You have different configurations of these distractors. So then these distractor it will be kept along this mandibular position, and you have unidirectional or it may be bidirectional sometimes. So based on the patient condition, then you are going to fix that in which configuration it is needed. So ultimately, your job is to say come out with this distractor device design, and based on the patient condition. So that is the thing, most important thing. Based on the patient condition is nothing but like say which we can see if the healthy person, so I should have this semicircular arch of the jawbone, but because she had an abnormality, which we can see, there is a deformity in the bone, and which it should be. If you see the facial center and the mandible center, definitely it is not at the same, it is not coinciding. So that's what you have this, we can find this deformity. And then how do you match that thing? That is thing where normally they do, which we can see and the other view. So the ramus height is this side, you treat this as a healthier side. So the height of the ramus portion is this much, whereas the defect size is very less ramus height, and of course which we need to say stretch or you need to lengthen this bone, the ramus bone, and incidentally we need to twist this bone. Why? Because the central the facial and the mandibular, you have a lot of offset. So then which we need to try to say say match that or align that with that facial center to the mandibular center. That's what which we need to do, and all that will be done. So that is to this patient only, not generalized surgical treatment normally they do. This is very specific to this patient, which that calculations and for that outcome of your design and development of your distractor. So that is purely based on this patient condition and these based on these models. So this we have published in one of the journals, like how Even we have simulated the CT parameters. Then from the CT parameters to the final um, printing of 3D printed parts, we have studied the deviations, how many deviations, so the errors are coming up. So anyway, so this is the initial condition of the patient. So before the operation, and or this is during the transformation of the surgery, but still you can find it is not 100% say symmetric, or rather than the still you can find, and still you can see there is a distractor here. This is there during the treatment, or this is during the transformation of our facial uh, region transformation, and it has been overcorrected as of now. Why? Because she's 8 9 year old only, but the bone growth will be there up to teenage, so it has been overcorrected as of now, but it should be finally corrected once she attains so 18 19 year old. So this is what your 3D printing technology helpful to plan the surgery, or do a rehearsal the surgery, or helping to design, develop a device which is unique, or which is specific to her condition or to his condition, any patient condition, that it will be helpful. And we have the next case study, the fourth case study. So this is ameloblastic fibroma of mandible. It's a cancerous bone reconstruction surgery. So the patient who needs or is a cancer bone, or this bone anyway, it's a cancerous bone which we need to remove it, which you can see this portion. So because of using that tobacco products, keeping that tobacco products here and chewing it, so which it has been spoiled, or it has, the cancer has been so here, which we need to anyway remove that bone. And say how do you get remove this bone, how much we need to get remove, and say normally they do a bone grafting. So the bone grafting, they will take a fibula bone, and they will try to say get this form by manually grafting it during the surgery, but it never happens such a close or that geometry. It may not be possible to attain, but that's what where this technology is helpful for um, designing the implant, which is specific and then more matched by biomatched or bio mimicked design. So here the you have the survived to defect side and taking it as a mirroring plane, and then it has been copied, and then how much portion we need to cut, where we need to cut, how much portion we need to cut. So this is the portion where it has to remove, and all that will be designed, and further it has been printed in 3D printed models, and it has been used for, yeah, this is the design we have done for this patient specific design, and we need to say attain the nerve relieving capability also here. Why? Because your that alveolar inferior canal that now will be passed from this condyle portion, and we need to provide the nerve relieving in this implant, and it should come and should again go other side of the condyle portion. So then we need to provide the nerve relieving of capability in this design, the implant design, and further it should be weight reduced, and further it should provide an osseo integration to the bone to the say implant. So that is also another thing which we need to understand. And we have suggested say a couple of designs to the surgeons to go about it. So then that should be even match or fit to the geometry of the patient. Luckily we have the CT data, or this has been, say, the implant has been fitted and tested, checking it for the fitment of it, versus the design. And further, we printed into with the polymer based desktop printers. And finally, we have printed with the metal titanium 6.4 material with lattice based design. So this is the thing, and you may get doubt even during our um, lab visit, virtual lab visit. Also, we have showed these implants that it has been printed here, and then you may get doubts. Then it should have been inside the patient mouth. Then how it has been outside? Yeah, then actually, this was our first attempt to implant the into the patient mouth, but we could not succeed it in the first attempt because of several clearances, or the ethical clearances which we need to get. There will be a certain formalities or which we need to apply and get it approved by the authorities. And if of course then some sort of regulator certifications and the qualifications should be given. So that's what where we stuck up here without implanting it. But anyway, this has been used for the surgeon to use it for the at least some extent during their conventional surgical procedure. Like to what they have done is we have supplied these models to the surgeons, and they have used their regular say the steel plates, bending on it, and then say using their regular say surgical instruments and taking this into an operation theater and say bending them these, and finally they have uh, resetted this bone, or they have cut, or they have removed this cancer bone from the patient mouth, and then they have used these plates that it has been practiced on the biomodel of the patient, and then they have done a bone grafting method here. But it has not a successful surgery. They have come with us recently, then can we reoperate it or reopen this? Why? Because this was not a successful surgery, because that bone grafting technique, the conventional surgical method, so may not succeeded this surgery to their expectations, but there are some complications or other things has came into picture. Then why? Because we had succeeded in other case, then that's what they have recently approached us to reoperate this. But in this way, wherever you have certain problems or the difficulties through a conventionally operated or surgical procedures, which it may not be able to serve um, the the sort of surgical outcome you are expecting, but it is not coming. So definitely the 3D printing will be the SOS for that kind of situations where you can make use of this technology. And the next case, we are a successful case, the successful story of say implanting it into the patient who requires a TMJ angolysis. So the TMJ angolysis is supposed to be the complex surgery as far as oral and maxillofacial surgeon is concerned. So why? Because we need to say design this joint, the joint where it forms. I'll try to explain. Yeah, this is the joint where you are able to the lower jaw and upper jaw, it forms a joint here, and with that joint, the TMJ, that's what we call as the temporomandibular joint, that is responsible for the articulation of your say jaws. So the articulation of the jaw um, is like normal opening is 5 to 6 centimeters. So this jaw has to play a vital role. And this patient, so by birth she had the fusion of the
this jaw bone, actually, which you can see. uh, this patient had the one side as fused by birth. She had a fusion of this joint, but not open joint. It is fused, but luckily other side has been normal, but the one side it has been fused. So because of that fusion of the joint, even she could not open her mouth normal, and even 1 centimeter. Then she used to manage with the fluids. So then she is a 19-year old. So then she has been surviving for the past 19 years so without opening her mouth uh, as a fuller extent, and then things like that. Then we thought that um, we can say take up this case, and can it be resolved through a long say a term pending case for them to conventionally they are unable to solve it to reconstruct that bone. So if you are not done that reconstruction properly, and again there will be a problem for her. So then that is the thing where we took this case along with our collaborators. Then this is what I was explaining. Like say this joint, um, it should be free, but it got fused by birth. So this which should be say cut this joint or detach this, and freshly we need to design this joint. So luckily she had other side as in a normal condition, and which it has given us to hint to say take that form, geometry, dimensions, everything has been copied, and once it has been destroyed, this joint, and freshly this joint has been designed here. So by making use of the softwares like Mimics and Trimatic software, so we have done that. And then we have this it will go in a 2-level surgery. So first level surgery, before we release this joint, now you can clearly see that this joint has fused, means it has become an integral part, but it never been like that, which you can clearly see that this is the other side of um, the joint, which it is free from this. It will be, you can remove this, it will come out then, which otherwise it is not happening here, which you can see it has become an integral part. This condyle has become an integral part of the zygomatic arch. So because of that, anyway, she could not able to open her mouth. So this is what our target is to say cut this portion, and freshly we need to design by taking this as a help or the so that's what. And before that, which you can see the alignment is not proper even with the teeth alignment, and then it's the reconstruction surgery like what we have done with the previous case. Here also it should be done, which you can see this is the initial condition, and they cut and they leave the bone to 1 mm, 2 mm, and slowly, which you can see 2 mm, 3 mm, and stretch forwarding this mandible slowly. So once it reached to around 19 mm, 20 mm around, so which it has been from the other side, the two sides. So one it is a 19 mm, another one 19 and 21 mm. So all that will be calculated based on these models. So how much the bone has to be stretched forward, all that will be done, and the designing based on that, designing this distractor device just previously also we have discussed. So that has been done here on these models. And once it has been done, so which we can see, so this is during the surgery, the transformation of the surgery. Initially 1 mm, 2 mm, this is 19 mm. So slowly it is stretching forward and keeping this as a distractor. And this is one side, and you can see the other side, um, which you can see here. So it has been stretch forward by making use of this device, and then finally from this condition to this condition, the initial condition, and the final condition. So which you can see it has been aligned, but the major part is left out now to say reconstruct or to dismantle this fused portion, and freshly we need to design this um, TMJ joint. And why this is so complex for a oral maxillofacial surgeon is you have a lot of nerves in and around your TMJ joint, and primarily you are going to say reconstruct the three say parts or the regions here. One is from the mandible side, that is condyle portion, and you have the fossa, means where it will go and insert onto the maxilla at the upper jaw side, and you have a zygomatic arch, so where it will become the arch like portion, that's called the zygomatic arch. So this zygomatic arch and this fossa and the condyle, which we need to design afresh, which we need to cut. Why? Because it got fused, and we need to do that. And this is what I'm talking about. So it should be cut, and then anyway, this is the defect side, and this is the survived side, or the other side, the good one, the side, and which we need to say do this reconstruction of this joint, and then taking this as um, the support with the survived to the defect which has been copied. And this is the initial design of that say condyle portion, and this is the design, and this is the initially we printed in a say a polymer based system. This we have filed a patent also, that is along with the Aditya and the other doctor, and he is my PhD scholar, and we filed a patent for this also, Indian patent. And we have this as a fossa here, like the fossa is also say captured from the survived to the defect side. So this fossa dimensions, the form, geometry, everything has been say taken from the survived to the defect side, and this is the design, and this is the one it has been printed further by medical grade PC through the polymer based 3D printing system. This has been printed, and this is what I'm talking about. This has been printed, and even this is a zygomatic arch, which from the maxilla side it will come, and the fossa where it is say will come from the upper jaw, and from the lower jaw the condyle portion, which we need to say fix it here, and we need to fix it here, and it will become a joint now. And in order to minimize the friction, means the metal to metal thing, and which it has been say placed a polymer here, biopolymer here, and this will come as a metal titanium 64, and this is what it's going to be. So initially, before we designed and printing it in a real implant, and which we printed these models and this implant designs, and further printed initially with the polymer based 3D printing system along with this bone, the lower jaw, upper jaw, and along with this implants has been printed. Yeah, and finally now it is getting fixed here like this. So it has been fixed here from the upper jaw side and the lower jaw side. And in order to better fixation, so then even we have designed a guide. So this is the guide we have designed for given it to the surgeon while performing the surgery and fixing this implant, the previously designed implant onto this, and making use this as a guide just for assisting or holding the drill bits or the tools they use to fix this the implant onto this skull. So the bone that the lower jaw from the upper jaw should be fixed here. Then this is the thing where it should be, and even we were there personally during this surgery, myself and my scholar and Professor Ian Gibson. Probably maybe might have used his book. Ian Gibson is a book from to manufacturing book, and we have a collaboration with him, and then we invited him with one of the visits to India, and then we fixed this surgery during that time. Then we were there, myself and Professor Ian, we are there inside the operation theater while performing this surgery, and we are the evidence for this surgery. And this is what where it has been now. We can see, so for the past 19 years he has been surviving in this way. You have this, once it has been released, the fusion of the joint, it has been released, and because that has been released, now you can see the normal opening of the mouth has been attained here. So that is has been done here. So yeah, and this is what we have designed, and it has been say fixed here to yeah. So this is with the help of that guide. So they have fixed these screws during the surgery from the maxilla side, the zygomatic arch. Now it has become the implant. Now it's a zygomatic arch, and now it has been fixed here from the top, and you have from the bottom. So you have these screws, and it got fixed during this. Say from the fixing from the bottom, that's a condyle side, and this is zygomatic side, and now she is doing good. So which you can see now, she could able to open her mouth, normal opening, normal biting, and normal chewing and normal biting action. Now she could able to do now. So for the past 20 years she has been survived in that way. But she has a better societal life after 19, 20 years. So she has been surviving in that fashion. But this definitely 3D printing technology will help wherever you have these long-term pending cases or any complex cases. Normally they could not resolve with the conventional surgical procedures. So definitely 3D printing will be the tool where you can make use of under these circumstances. And let me come to my last case study, the sixth case study, that is a basilasio integrated implant. So this basilasio integrated implant is this is an accident case, so which we can see the condition of the patient after accident. So you met with an accident, and incidentally he lost 5 teeth along with the bone. So he has lost, there is a partial damage of the bone, the maxilla bone, and the 5 teeth has been say he lost, and then which we need to fix the 5 teeth here, and we need to attain the nerve relieving capability also. And the challenge here is the conventional uh, uh, the implants that are available from the market may not be say sufficient, or rather than it won't fit here. Why? Because if you have a support, bone support, then you can fix some 4 or 5 say screws, and then you can fix the teeth, but that is not the case here. So anyway you are not able to use the traditional or the conventional implants that are available from the market. I'm talking about this kind of implants. So then anyway it won't serve the purpose here. Then for that reason, so 3D printing will enable us to indigenously design this implant, which will unique, or which will required for this, means which you can see this is an asymmetric fracture. So which this is an accident. We don't know whether he is going to broke his thing as a symmetric nature. So if it is symmetric, then it may be easy job for us to design an implant. But here it become an asymmetric fracture. So then accordingly we need to design the implant. Like say you have the base plate connectors and abutments. So all that, which you can see, this is a different dimensions and the shape altogether because of that, say, asymmetric nature, right? So this is what it's going to happen. And we have even tested with the say we have done the finite element analysis for the checking of this failure analysis for this implant, and the fitment, everything we checked, and we finally initially we printed with a polymer based thing, and then we have given this. It's basically a desktop based polymer printer we have used to print this initially to check, and giving it to the patient, the doctor, to rehearsal or where they want to cut, and during the surgery what they are going to do, let them do all that stuff here, and at least they could able to even come out with a 4 teeth, not even a 5 teeth, but at least it's okay that it has been accommodated 4 teeth. So like that they can come out with before going to the operation theater. So they have this opportunity what they are going to do, and that's what they got this opportunity here, right? And immediately, so this is the implant. It has been fabricated, say, which it has been done here. So this is the support structure, and this is the implant, and this is along with the support. And after removing the supports and following all that regulations, then this is the implant after doing sterilization and then taking it into the operation theater. And this is during the say the surgery and how it has been fitted. So initially it has been, and then finally it has been fitted into the right placement of here. And this we have published, this case study is one of the reputed journals of rapid prototyping journal. So we have published. Somebody interested, you can for this article also. And this is what our implant is there. It's a post-operative say image. So how your implant has been fixed, and on top of it the teeth, how it has been fixed. And this is the sixth case study. And as you can see, several cases that abnormal growth of the patient, or the cleft cases by birth, or some trauma cases where, but we need to know our strength, or the readiness of taking this or accepting these cases to deliver your services to the surgeons. Sometimes if you could not able to some emergency cases, some the head injury, severe head injury, but whether it could able to say supply this model or implant in a right time to the patient as well as to the surgeon. So that is the major challenge here to lies, whether you want to take up that case or not, right? If it is a long-term pending cases, not a emergency case like these tumor cases or the cleft cases, those are not emergency cases, but there are some emergency cases which we need to say even check it. And let me come to the concluding part, or the future direction of this 3D printing in medicine. It is undoubtedly the organ printing. Now it has been initially started now. So it is the technology got triggered. If you see that the hype cycle or the Gartner cycle, but this is the technology, just it has been triggered. But it will take minimum 20 years, 25 years to reach to an industrialization or a plateau stage, the plateau of productivity you call. So it will take a lot of time, maybe 20 years to reach that. But anyway, we'll understand what is this say tissue engineering or organ printing is all about. So then they will take the material as from the patient own as a living cell. So the living cell, it will act as a material here, no synthetic material. Everything is a natural material here. That too, it is a the kind of say the blood cell, or the living cell, any living cell that they are going to take, or stem cells, or any living cells they are going to take here from the own patient body, and they will prepare the material or a ink kind of a thing here to say make use of that as a material, and then the process remains same. Like if you are targeting to an heart valve or a heart ventricle, so then
Hello, participants. There was a internet issue in the institute. He's going to join quickly. Just be in the meeting.
Hello, are you able to hear me? Hello.
Hello, sir.
Yeah, actually there is a network issue, right? So
Yes,
anyway,
sir.
I have concluded my talk. So if anybody is having any questions, so they can ask.
Yeah, participants, you can unmute yourself, and if you have any queries, please ask the speaker.